all the way up to 0.6, which is on the proton-rich side, so slightly proton-rich conditions. So how do we model the R process nucleosynthesis? And we have collaborators that perform these hydrodynamical simulations, and the model that I will share with you today includes 2 equal mass mergers, and they in this model we see that about 2 times 10 to the minus 3 solar mass of material is ejected dynamically. So what I study will show you today is the dynamical material. What is very interesting in these hydrodynamical models is that these weak interactions have been included, as was emphasized earlier today. They are very important to determine the neutron richness in the material. So if we have the capture of neutrinos on free neutrons, we can actually decrease the amount of neutrons, or this the inverse reactions can have the opposite effect. So what we do is that we receive these the time evolution of small mass particles, or trajectories, that's we call them. We have the time evolution of the temperature, the density, the entropy, and also the electron fraction of each of these trajectories. So we have about 800 trajectories for the model that I will discuss to you today. So we don't have one single electron fraction, we have a range. And here on the y-axis, we have the mass fraction. So you can see that most of the material is quite centered around 0.3 in electron fraction. But the tail goes all the way up to 0.6 and down to 0.05. So in a moment, I'll show you a movie of one such R process calculation. Here, I just want to show you the axis where we have the nuclear chart with neutron number on the x-axis and proton number on the y-axis. And here, each box is the isotope, and the color scale gives us the abundance. So I'll start the movie here. We can also see the temperature evolution and the density evolution for this specific trajectory, which is just an example of a very neutron-rich trajectory. And then you see the evolution of the abundance here, mass number versus molar fraction. And we can compare to the solar R distribution here in blue at the top. So we do one such nuclear network calculation for all of our trajectories, and we do a mass average sum to get the final results. So how do we study the impact of neutrinos? And for this, we have created a case where no weak interactions have been included in our model. And we can compare this to our most sophisticated model, which includes the weak interactions. So you can clearly see a difference in the initial composition. So this is at the time when we start the nucleosynthesis network, where the mean value for the model without neutrinos is about 0.13, but also with a wide distribution. And when we include the weak interactions, we have a mean value of about 0.27. So using this as input to our nucleosynthesis network, we see we get these results. So first of all, I'd like to emphasize that our model, including the weak interactions, have a quite solar-like distribution all the way down to about A equals 90, while the model for non-neutrino interactions have a larger, do not have this production of the lighter element. So the discrepancy is about mass number 120 or 30. And it produces a larger amount of the heaviest elements and also the actinides, as you can see here. So if I change the axis from mass number A to mass fraction here, and I have the proton number, and we have summed over each isotope for all the elements. I just want to highlight here the fact that our model that includes the weak interactions or neutrinos have about 14 times larger production of strontium. So that's very interesting, and we'll hear more about the detection of strontium later by Camilla Hansen, so I'm looking forward to that. And then I would like to talk to you about the angular distribution that we see in our models. So here I've highlighted the polar regions in pink. So, and then we have the equatorial plane in green. And in the middle, we have the middle ejecta, I call it. So just to give you a picture here of the material, how the composition is. If we just look at the angular distribution, we see that, in fact, most of the material is ejected in the equatorial plane, as we can see here on the y-axis. And but it is the material in the polar regions which reaches these extremely neutron or even proton-rich conditions. So the mean electron fraction is a lot higher in the polar regions than compared to the equatorial plane. But the most of the mass lies in the middle ejecta. And this is also reflected in our final results for when I look at each angular region. So to the left here, we have now the models without neutrinos, and to the right, the neutrino model. And the biggest discrepancies between these two models we can see is in the on the pink curve here in the polar regions. And this is where the post-merger remnant has the emission of neutrinos of the post-merger remnant has the largest effect. So one of my last points that I would like to talk to you today is the heating rate that we see from the radioactive decay of the freshly synthesized R-process elements. So here on the this is the Q value on the y-axis, and we look at the time scale of days. So first we see a bump of about, for both models, it's a slight increase in the heating rate here due to free neutrons, which are left after the completion of the R process, and they decay after about 10 minutes due to their half-life. And then we have a discrepancy at a later time between the two models, which are in fact due to the beta decay. And we have also discrepancy at a later time, around 10 days and later, up to 100 days, where we see that the model that does not include neutrinos have a larger heating rate here at late times, and this is due to alpha decay and fission of species, trans-lead species, which, as I showed you earlier, this model also produces a larger amount of the heaviest elements. So this is reflected in the heating rate, and this curve can be also converted together with other models to create a light curve, as discussed earlier today. So this is very interesting that we can see the discrepancies between the models of that includes neutrinos or not. So I see I will go to my conclusions now. So in our work, I did not show you already because of time restrictions but we did study 4 different models, not only symmetrical mergers, but also asymmetrical mergers, and also 2 different equational states. And it's we see that our results are quite independent of both system mass symmetry and equation of state. And this is very favorable for extracting ejecta mass from kilonova observations. And the impact of neutrinos, we see that we have a very solar-like composition down to A equals 90 for our model, including the neutrinos, compared to 140 without neutrinos. And it's a very significant enrichment in strontium. So this is very interesting. And yeah, then I would like to thank you for your attention.
Oh, okay, thanks a lot.
Great, thank you.
Very exciting, yeah. So Gianluca,
yes,
moderating.
Hello everybody, Gianluca Pizzone speaking. So I would like to present you two questions which arose and are on the chat. The first one from, can you hear me well?
Yes, I can hear you.
So the first one is from Steven Rosberg, and they said, in the simulation that you are mentioning, just at all, it seems, you showed a LIGO picture. What is the used neutrino transport or the approximation that you used?
What is the, sorry, can you repeat the last part of the question?
What is the used neutrino transport or approximation that you used?
Okay, so first of all, I'd like to clear up that it is not the simulation of Just et al. 2015 that we are using for our model. And the neutrino interactions are, or transportation is what is published by Ardevol Popillo 2019. So it's the ILEAS improved, sorry, I don't know the abbreviation perfectly, but it's improved leakage scheme, but it also includes this module for neutrino equilibration in high density regions and free streaming, also approximations for free streaming regions. So it's quite newly updated work.
Oh, okay, so then we have a second question from Andreas Kohn. We know that weak interaction take place, and the results seem to support this conclusion. Are these results particularly uncertain?
Well, it's a bit difficult to quantify exactly how uncertain these exact results are compared to other results, because we all rely on quite heavily on theory. So of course our result would change if I used a different nuclear library or something like this. But as you can see here on my conclusion slide, the results are very independent on, at least for these two equation of state. So sorry, it's a very small figure. DD2 and SFHO is what we used. And even the asymmetry, we did analyze models with 1.25 solar masses versus 145 solar masses. And the results are very, very similar. So in that sense, it's quite insensitive, but of course there are a lot of uncertainties in these kind of models.
Okay, then I don't see any other prompt questions, so I send the ball to Konrad.
Thank you.
Thank you.
And thank you, Ina, again for this nice talk and answering these questions.